Hi, so in this video we will discuss the phenomenon of electromagnetic induction. You will shortly see what that is. I will begin by some experiments which will dramatically illustrate what induction is. Okay, so first of all, imagine this is a source of an upward magnetic field. Okay, like this may be a pole of a big magnet, big and strong magnet, and the opposite pole is up here above the camera so that you can see it though. So think just that there is an upward magnetic field, uniform magnetic field here, and we bring a conductor coil here. Okay, this paper assume you can assume to be a conductor. Okay, I bring this here, and quite obviously you will see that there may be no current in this. Okay, since there is no voltage, I have not connected to a battery or anything, but you will see interesting things when you actually move this conductor, or maybe when you shift, or when you squeeze it, when you stretch it, you will see something interesting. Okay, so when you actually compress it, or when you stretch it, you will see that some currents are produced in this coil. You can see that maybe by connecting it to a galvanometer, or maybe placing a bulb here or anything. But you will also see that the direction of current when I uh, did this would be different than the direction of current when I did this. Okay, and if this were an electromagnet, okay, and you will also find currents generated in this coil if you actually decrease the magnetic field or increase the magnetic field. In both the cases, the direction of the current would be different. Amazingly enough, you will also find currents induced in this coil if you actually shift this coil like this or like this. Okay. Well, at the first thought, you might think this is quite impossible. How could electrons gain power? I don't know. How could electrons start moving quite all of a sudden, though no voltage, seemingly no voltage was applied? As you know, current cannot flow without potential difference, so some potential difference must have been generated in this coil by doing any of these activities, these, or anything else, okay, or by reducing or increasing the magnetic field. Well, so these experiments lead to some law, okay, which is called the Faraday's law. What it says is that induced EMF, which is denoted by the symbol, I will tell shortly what EMF is, that is equal to negative, oh man, negative d phi b dt. Phi b is nothing but magnetic flux. You will also see what that is shortly. And okay, for phi b, or magnetic flux, let us go back to our discussion of electric flux. Then we considered a fluid flow analogy and said that what flux is the rate of flow of something across a surface. Okay, so when we consider fluid as the flowing substance, then we saw that the rate at which the volume flows to the area is equal to the velocity times the area if the area is perpendicular to the velocity, and is equal to VA cos phi when the area is not perpendicular to velocity. Let's also quickly review how we got these formulas. Well, let's assume the fluid was moving at the speed 2 meters per second. Okay, the volume flow rate dV dt well, if the volume flow rate is constant, we can also think of this like this. The certain amount of volume flowed, let's call that delta V, in certain amount of time delta t. Okay, and when we take the time interval equal to 1, okay, so by this formula we will get the volume that flowed in 1 second. Okay, so say this fluid here moved at 2 meters per second. The length of the column that moved here, column of water that moved here, would be 2 meters. Okay, and the volume of that water that flowed in 1 second would be 2 meters, which was the velocity, that is the distance it traveled per second, times the area. Okay, since the volume of a cuboid is area of base times the height. Okay, so it would be V times A. So this would be the volume that flowed per second, or the volume flow rate. uh, and when the area is not perpendicular to velocity, the volume flow rate will no longer be VA, since the fluid is not flowing in that direction. Okay, it's not flowing in the direction of area, but it's flowing in this direction. So the fluid will actually cross only this area, which is the component of area that's perpendicular to velocity. Okay, which is A cos phi in this case. So it's the volume flow rate is V times A cos phi, which we represent by the dot product, or V dot A. Okay, which is nothing but Va cos phi. And when we replace V by the electric field, we get the electric flux as Ea cos phi. So this was electric flux. When we replace this E here by B, or the magnetic field, what we get is the wait what we get is the magnetic flux, that is Ba cos phi, if the magnetic field is uniform over a flat area. And if it's any random curved surface, you do again the same trick. You divide the surface into many small flat areas, dAs, and then you sum the B times the small area dA times cos phi over the whole surface, which you represent by this long S, or the integral. Okay, so that's not very important for our understanding here, though basic understanding. So I need to clarify certain things about flux. First of all, we have, say, any closed conductor loop. We have to assign the direction of the area vector. Okay, so first of all, you need to specify a direction in which you would want A. Okay, so I say maybe this is the direction of my area, perpendicular to the plane of this loop. Okay, then if then the field is like this, in this direction, then I would say that the magnetic flux is positive, because the component of the magnetic field in the direction of area is positive. Okay, how is that? Well, what do you mean by component being in direction? Say the area pointed here, the B also pointed here, the magnetic field. So you say, well, oh, sorry. We can easily see that from the formula for flux. Magnetic flux equals, through a flat surface, equals Ba cos phi. Phi is the angle between the area vector perpendicular to the area and the magnetic field vector. Here in this case, A and B are both in the same direction, so the angle between them is 0, and when we put 0 here, cos 0 is just 1. Therefore, the magnetic flux is simply the product of the magnetic field times the area, which is both positive in this case. But when the area we choose to be in this direction, by choosing the direction of area we mean in what direction are we measuring flux. Okay, then if the magnetic field pointed in downward direction, then we would say that the magnetic flux across the surface is negative. Why is that? That is because I chose the area vector to be in this direction. That is, I want to measure the flux in this direction. Well, B doesn't go in this direction, it goes in the opposite direction. Therefore, I must say that the flux here, magnetic flux, is negative. Okay, and you can also see that since the angle between these two, since they are opposite, the angle between these two is 180 degrees. Okay, they are quite opposite. And in the formula, when you put cos 180 degree, you get -1. If you don't know cos 180 degree is -1, don't worry, I'll make a video on that. Okay, yes, so here the flux is negative. Okay, if instead we had chosen the area to be downward and the magnetic field was still downward, the flux would be positive since B dot A, that is BA cos phi, was positive. Okay, and about this EMF here, EMF will be the same as voltage if your voltage source is an ideal one. By that I mean uh, when we have a circuit, some resistors here, and when we have a voltage source, if we can ignore the internal resistance of this cell, the actual cells also have their own resistance. If we can ignore this, then the voltage that this cell will provide will be equal to the battery EMF. Okay, so here the induced EMF can be imagined to be the induced voltage. Okay, uh, you can actually skip the details anyway. So, and again we have d phi dt here. This phi b represents the magnetic field. As I had told in the first lecture, this dy by dx, here y is magnetic field phi b and x is just time t. Okay, this thing will represent the rate at which this above thing changes with respect to this down thing. Okay, so here this represents the rate at which the magnetic flux changes with respect to time. Okay, so just like the speed is positive when uh, just like the speed is positive when we covered positive distances in time intervals, the rate of change of magnetic flux would be positive when the change in magnetic flux is positive. Okay, so for example, here we have a loop, okay, and I assign the direction of A as this one above it. By assigning the direction of this A vector, area vector, what I am saying is that I want to measure upward flux. Okay, suppose the B field is in this direction. Okay, you can see that it has a positive flux since we are measuring flux in this direction and the field actually goes in that direction, though it's not completely in that direction, but the component B cos phi is still in that direction. Okay, so the flux is positive, and also you can see that from the formula, since the angle phi between them is acute and the cosine of acute angles is positive, this whole expression will be positive and the magnetic flux would be positive. If you then have any problem in this, leave it, actually doesn't matter. Okay, so yeah, when we have a magnetic field like this and when it is increasing, okay, we would have d phi dt as positive, just like when we have an origin and we are measuring distances from it, and when we keep increasing distances, we say that we have some positive speed. Okay, because the change in distance divided by change in time would be positive, since we cover positive distances in positive time change. Okay, time change just cannot be negative anyway, so I said nonsense. Okay, forgive me. So yeah, since flux is positive and becoming more positive, since the B is increasing in magnitude, so you can see that in the formula BA cos phi will also increase, thus the flux will also increase. Since it increases, the rate of change of it is positive. Okay, so by the formula you can say that induced EMF is negative d phi dt, and since d phi dt is positive, you can say that induced EMF is negative. Okay, now what do we mean by induced EMF negative? Well, whenever the induced EMF you get negative, what that means is that when you curl your when you align your thumb with the direction of the area vector, then if you get a negative EMF, the direction of the EMF is opposite to the direction in which your fingers curl. I chose the area vector to be like this here, so, and my fingers curl around this direction, so the induced EMF is opposite to it in this direction, that is this direction. Okay, and also note that the direction of induced EMF is same as the direction of induced current, so this also tells you the direction of induced current. Okay, induced current is just the current which originated by changing the magnetic flux. Sorry. As another example, take this case. Again we place the area vector in the same direction, and again we have some positive flux due to this field. Okay, because we are measuring flux in this direction and field actually is going in that direction, and when it decreases the flux also decreases, since in the formula BA cos phi B decreases, therefore the magnetic flux decreases. Now since it decreases, you get the rate of change of flux negative, just uh, just like when we have, say, when our speed is decreasing, we say that we have negative acceleration. Okay, similarly when the flux is decreasing, we say that its rate of change is negative. Okay, now since d phi dt is negative, the negative of something negative is positive, so we can say that induced EMF is positive in this case. Okay, so yeah, the positive value of EMF means that the direction of induced EMF or the induced current is same as the direction in which your fingers curl when you place your thumb in the direction of assumed area vector. Okay, I chose the area vector to be there, that means I wanted to calculate flux in this direction, then the induced EMF will be in this direction. Okay, like this, because the induced EMF came out to be positive. So a conclusion is that when the magnetic flux is increasing, d phi dt is positive and the induced EMF is negative. And what we mean by a negative EMF is that in whatever direction you placed your thumb to be, that is in whatever direction you chose to be of the area vector, the direction in your fingers, the direction of the fingers curl, you take the opposite of that direction, and that would be the direction of EMF if the EMF is negative. If the EMF is positive, then you retain the direction in which the fingers curl and call that the direction of induced EMF or the induced current. Well, if you find this discussion uh, well, if you find these things difficult to remember, Well, you have a law to save yourself. Lenz's law. This is actually much simpler law which can help you find the direction of induced EMF. Let's see what it says. Okay, so what is Lenz's law? It says that any induction effect is in the direction so as to oppose the change in magnetic flux. Now what does that mean? By induction effect we mean the induced current or the induced EMF. Okay, so uh, for example, when we move a magnet with north pole downwards towards this coil, that is, its velocity is in this direction, you can see that the magnetic flux in the downward direction increases. Now why is that? You can see that the magnetic field lines from the north pole come out like this. Okay, and you know that they are closer together near the pole than outside it. So when the magnet was here, the field here was weaker, and when you bring this magnet closer, the crowded lines will cross this surface. Therefore the crowded lines represent stronger magnetic field. Therefore you actually increase the magnetic field through this surface. So since you increase the magnetic field, as the formula for magnetic flux B A cos phi for a uniform field over a flat surface will tell you that the flux also increases. Okay, though this field is not uniform here. Okay, even for non-uniform fields you can see that when B increases, the magnetic flux will also increase. Okay, so you can see that the downward flux increased. So the induction effect should be such that uh, flux downward should decrease. Since the downward flux increased, the Lenz's law will try to reduce this effect and produce a flux in the opposite direction. Okay, so by moving the magnet down, we increase the downward flux. So actually the upward flux should increase. Now how can that happen? If we run the current in this direction and use the corkscrew rule, we will see that when the current goes like this, the field lines are like this. So you can see that the field would come out of the loop like this if the current went like this in this direction. If the current went in this direction, then the field would be like this. So the field in the opposite direction reduces the flux in the downward direction or increases the flux in the upward direction. Okay, by both viewpoints you can see that the downward increase in magnetic flux was opposed by this thing. So using this neat law, we can find the direction of induced EMF. Let's take another example. When we have the south pole here, the magnetic field lines are like this, and when you move it upwards, so in this case, when we have the south pole aligned downwards and the magnet moves upward, you can see that the upward flux decreases. How is that? Well, earlier when the magnet is here, the field were crowded together and pointed in the upward direction. When I move it above, they still point in the upward direction, but they are farther apart. Okay, they are farther apart, so the upward flux is lesser since the upward field is lesser. Now saying that the upward flux decreased is same as saying that the downward flux increased. How is that? Well, when we consider the downward flux, uh, that is, we say that we choose this area vector, then the flux of magnetic field here would be negative, since B is not actually going in this direction, it's going in the opposite direction. Okay, so the flux would be negative, and moving the magnet above will reduce the value of B, that is make it less negative, that is the downward flux will actually increase. Since in both these cases downward flux increases, the induced current tends to decrease downward flux or increase upward flux. Okay, so again, to decrease downward flux or to increase upward flux, uh, the field should go like this to increase upward flux, therefore the current goes in this direction like this. Okay, so that is how you can use Lenz law to find the direction of induced current. Now I would like to end this video by explaining briefly what a transformer is. Well, so a transformer basically consists of two windings, the primary winding and the secondary winding, and a conductive path like this, okay, with insulations at the boundaries. So what a transformer does is that it reduces or increases the voltage in an AC circuit. Okay, what is an AC circuit? In an AC circuit, both the direction and amplitude of current oscillates with time. Okay, so at one time the current would be in this direction, at the other it would be in the opposite direction, and also the magnitudes of current would change at each instant. Well, so when we apply AC voltage, that is changing, alternatingly changing mm, voltage across this winding, the current also would be changing across this winding. Since the current changes, the flux due to these currents also will change across this winding like this. So for example, when the current increases, the magnetic field strength will also increase, therefore the flux through this will increase or decrease depending on the direction of current. So briefly, a change in magnetic flux is caused here. This will induce currents in this path, and this changing currents here will uh, these changing currents across this secondary winding will cause changing flux in this winding.